Title your notes Non-Proportional Dimension Change. So Wednesday's lesson, what we learned was proportional dimension change. Today, our short little lesson is going to be non-proportional dimension change. What in the world does that mean? What do you think non-proportional means? And what are we going to be doing today compared to what we were doing on Wednesday when we did the perimeter area volume ratios? Okay, so what do you think? I can kind of show you what I mean. On Wednesday, if we wanted to use our perimeter area volume ratio trick, aka able to answer the question without touching our formula chart, right? We were finding the difference in the volume of cones, but we weren't using the cone formula. We were finding what happens if we half the radius of a cylinder, but we weren't using the cylinder formula. So we were able to use that trick on Wednesday. But something had to be true to be able to use them. You all got it. They had to be proportional, but a better word is our figures had to be similar. So to use our trick, to use our 1D, 2D, 3D, going back and forth between dimensions, our figures had to be similar, and that was important. Had they not been similar, then we wouldn't have been able to use that trick. We would have had to use the formulas on our formula chart. No shortcuts. Okay, so you can write some examples down if you would like. Here's what it would look like if our figures were not similar. I did not do this to you on Wednesday, on the last lesson. I want you to double the height, but don't touch the area of the base. We didn't do any like that. I want you to add 3 to a cone's radius, but keep the same height. We didn't do any like that. I want you to triple a pyramid's base area, but then I want you to half its slant height. Whoa, we're not in Kansas anymore, huh? So these are examples of non-proportional dimension change. That's what it looks like. So if you wanted to summarize this, on Wednesday, whatever we did to one dimension of a figure, we did it to all the dimensions. Today, we don't have to do the same thing to all dimensions. We can just affect one of the dimensions or 2 of the dimensions. We can affect one dimension one way and another dimension a different way. So that's what's different about today. All right, let's see what we can do with this. I have 4 examples, and I want to decide if these are proportional change or non-proportional change. Are these figures similar or not similar? Let's start with this one. Proportional, not proportional. So even though I am tripling the radius, I didn't touch the height. So even though the radius has a scale factor, the height doesn't have a scale factor. Therefore, I have not changed this cylinder proportionally. It is not proportional. Oh, I just ungrouped that. That was cool. So this would fall under today's lesson. Okay, what about this one? Okay, you're saying proportional, but what if you only know that I changed the height. What did I do to like the length and the width? Oh, good one. I put that in parentheses and it's really hard to see. It's a cube. So if I change one dimension, boom, I'm changing all the dimensions because you can't change it. They're both cubes. So you can't be like, oh, now it's a rectangle, not a square. So yeah, good. That one's proportional because if you change one, you change them all. Okay, what about this one? Proportional or non-proportional? Do you know why I'm pausing? Because you're all getting it wrong. Okay, let's talk about why this one is actually not proportional. I realize that I did the same thing to every dimension, but what is the problem here? Good, Aaliyah. I added, guys. I didn't multiply. To be proportional, you would need a scale factor. On this one, what's the scale factor? Times 4. On this one down here, what's the scale factor? When you create similar figures, you have to multiply everything by something. It can be by a fraction, a whole number, a decimal, but it has to be a multiplier. It has to be a factor. On this one, when I add something to every side, that's awesome that I did the same thing to every side. But that, well, it's not a cube. That rectangular prism would not be similar to my original one. Okay? And the key word was that, yeah, we're adding. Adding and subtracting, not proportional. All right, last example. Where does this one go? So multiplying and dividing go together. You're allowed to do it. I took the height and I halved it. I took the radius and I halved it. Therefore, those figures are similar. Because the scale factor, if you can say the scale factor, they're similar. The scale factor is times 1/2. True or false? A sphere will always be similar to another sphere. It is true. Let's take it, let me kind of give you a little bit more insight here of what we could do. So if I called this the length and the width, and then I made a new one, and this is 3L, and this is 1/2 W or something. Okay. Are those two proportional? Are they similar? No. What's the scale factor? I don't know the scale factor because I did one thing to the length and I did something else to the width, right? Now, try to do that same thing with a circle. Try to do that same thing. Try to make those circles not proportional. Well, in this one, the scale factor is 2. If I had written 5R, the scale factor is 5. Can I make two circles not be similar? The thing is, they don't have a length and a width. They don't have a height. And so it's impossible, it's impossible to make two circles not be similar. They're always similar. So with the same reasoning, a sphere is always similar to another sphere. The formula for the surface area of a sphere, how many variables do you see in that formula? There's only one variable. I can't change one variable by something and the other variable by something else because there's only one variable. I think I've talked enough about spheres. Okay. All right. So let's kind of dive into what it looks like when we change one dimension but not the other. If only the radius of the cylinder is doubled, how will the volume be affected? Now, when you get a problem like this, I don't want you to use numbers. I don't want you to use, I don't want you to plug anything into a formula. I just want you to use the formulas, and I want you to compare them. So I want you to always start by writing the formula. Volume of a cylinder is base times height, but I'm going to be more specific. It's pi r squared h. Now, what did I do? I doubled the radius. So the volume of the new one is pi, I think we did this in an example on Wednesday, pi 2r squared h. Let's cross out everything that's in common. Pi, you're in common, you're gone. H, you're in common, you're gone. I've got r squared left, not equals, sorry. I'm comparing, not equaling. And I've got, ooh, what's 2r squared? Well, 2 squared is 4, and r squared is r squared. Okay. Cancel out what we have in common. There's an understood one there. How will the volume be affected? The volume will be 4 times bigger. So I doubled the radius, and I quadrupled my volume. Now on Wednesday, if I had doubled the radius and doubled the height, then I could have found my answer without even using the formula. Oh, I just take my scale factor and I make it volume. I cube it. But on this one, we had to plug it into the formula and see what happened. That's a good question, Neil. I can't cube it because I only affected the radius. I didn't touch the height. And that's why we can't do what we did on Wednesday. So that's why we don't do this on a problem when it's non-proportional. Okay, let's try this next one. If only the height is doubled, how will the volume be affected? Let's do the same thing. Pi r squared h compared to pi r squared 2h. Let's cross out everything in common. Pi, you're gone. R squared, you're gone this time. And H, you're gone. Wow, this one was easier. So if all I do is double the height, then I just doubled the volume. Because height, how many times does height show up in the formula? Once. How many times did radius show up in the formula? It showed up twice. That's why this one is times 4 and this one's times 2. Do you have to memorize that? No. Can you just plug it into the formula each time and then compare? Yes. So don't feel overwhelmed. Okay, last one. If the radius and the height are both doubled, how will the volume be affected? We are not even going to do this one because we know, okay, if we're going to change all the dimensions, if they're going to be similar, then we get to use our old trick and we don't have to touch our formula chart. Okay? Okay. We already did this question on Wednesday, right? All right, let's try this one. When inspecting two tissue boxes, you notice that one has half the height and triple the width. How do the volumes compare? Some of you could probably do this one without the formulas, but we're going to do it with the formulas just to see how we feel about it, just to feel good about it. Okay, how do you find the volume of a rectangular prism? Technically, it's base times height, right? But we know it's a rectangle, so the area of the base is length times width, so we're going to go with this. So we're comparing length times width times height to length times 3w times 1/2 h. Is everyone okay with where I got those? It said to triple the width, check. And it said to half the height, check. Everyone okay here? All right, let's cancel out what's in common. L, you're gone. W, you're gone. H, you're gone. There's an understood 1 left, and what's left over here? So that's like saying 1.5 times bigger volume. So it doesn't follow the rules from 1D, 2D, 3D, but it is able to put the factors into the formula and cancel things out. 1.5 times bigger. So these are the easy ones. When you half things and triple things and double things and times 5 things, when you're multiplying, these are the easier ones. Let's try one where we're not multiplying. A gift box has dimensions 6 by 8 by 12. If we cut the height in half, but add 4 to the width, this is where we're going to be in trouble. How do the surface area and volume, how are they affected? Okay, this is our last problem, promise. Let's go through this. I want you to find the surface area of the original one and the volume of the original one. Divide and conquer. Try to get it quickly. Volume is definitely the easier of the two, right? We can all multiply numbers in our calculator. Who's going to be first with the surface area? Let's see. Awesome job. Okay, so that's old news. We just found the surface area and volume of the prism. Okay, now the new prism, the new one, has half the height, so the height is 6. The length will keep the same. Now, this is what's kind of cool. I don't care which one's the length and which one's the width. I can add 4 to 8 or 6, and you'll come up with the same answer. Trust me, I promise. So we'll do, I don't know, the length is 8, and the width is now not 6, but 10. We did plus 4, and we did divide by 2. Here's the new dimensions. Now I want you to find the surface area and the volume with the new dimensions. Volume's the easiest. Good, the volume is 480. Who's going to get that surface area first? Good job. Surface area, 376. You're going to be mad at me when you discover we did all this work for this. Here's the deal, guys. On the other problems, we were able to summarize it. Oh, the volume was 3 times more. The volume was 1.5 times more. When you throw this word, adding or subtracting, into the problem, it's no longer pretty. You just have to find the surface area of the old one, you just have to find the surface area of the new one, and then you just compare them. How do you compare them? I don't know. You have to see what the problem tells you. Sometimes it'll be like, how much more surface area does it have? What would you do? 376 minus 432. Or vice versa. You'll get a negative answer, but it doesn't matter. So 56 square centimeters more. Sometimes you might subtract them. Sometimes it might say, you know, how many times more surface area does it have? So 432 divided by 376, or maybe the other way around. Maybe it would be 376 divided by 432. See, I told you you'd be mad at me because these are not pretty. These are not cut and dry. So it either got smaller by 0.87 or you could say it got larger by 1.14. What I'm saying is that when you add and subtract, all bets are off. The connections are not the same. You have to find the old, you have to find the new, and then compare it however the problem asks you to compare it. Sometimes you'll subtract, sometimes you'll do a ratio, which means divide. Is that okay?